In this video, I'm going to demonstrate a matrix multiplication operation using Apple's Metal Performance Shaders framework. And in my previous video, I introduced the Metal Performance Shaders framework and its compute flow concepts, so if you haven't watched it, you can click on this link. So we can begin by importing the Metal Performance Shaders framework. Then we have to create an instance of a device that supports Metal. So we can use the Metal create system default device function to do that. And this function returns an optional Metal device. So I'm going to force unwrap it because I know that my device supports Metal. But if you're uncertain that your device supports Metal, you can just use the MPS supports Metal device function and returns a simple true or false. Or you can use the Metal copy all devices function to get a Metal device array of all Metal supported devices in your system and use them however you like. But for simplicity, I'm going to force unwrap everything. Now that we have our device, we can create the command queue so that we can queue up command buffers. And with the command queue created, we can create the command buffer, and this will allow us to encode commands. Also, you're not limited to using only one command buffer per command queue. You can create multiple command buffers with each having commands, and the command buffer that you commit first to the queue will be executed first. So now that Metal is set up, we can begin our matrix multiplication operation. To start, we need to create three matrices, one for the left side of the operation, one for the right side, and another for the result. The matrix on the left side is going to be an M by R matrix, and the matrix on the right side is going to be an R by N matrix. So the matrix on the left side's column must be equal to the matrix on the right side's row, which is R. And the result matrix is going to be an M by N, where M comes from the row of matrix A and N comes from the column of matrix B. Now let's define the multiplication operation that we're going to perform. We can define A to be a 3 by 2 matrix, B to be a 2 by 3 matrix, and C is going to have to be a 3 by 3 matrix. And these are just some made up matrix sizes, and I'll make up some entries for them later on. Now we can make a matrix multiplication kernel. I'm going to pick the initializer with the most options. Then I can clean up this code a little bit and start inserting some values. For the device, we'll put the device we made. And for the left and right matrix transpose, we'll put false because we don't need it. But even though we don't need it, I'll go ahead and tell you what it does. Let's say you have some matrix A with entries in it that make it a 3 by 2 matrix. Then this matrix's transpose will be a 2 by 3 matrix. And the entries will be the same, but reflected. So matrix A's first column vector is going to be its transpose's first row vector. And matrix A's second column vector will be its transpose's second row vector. And that's basically what transposing a matrix is. So let's continue filling up this initializer. For the resulting rows and columns, we're going to use matrix C's row and column amount, because that's the dimensions we came up with for the result in this example, which are both 3. And for the interior columns amount, it's going to be R, which in this example is 2. And we'll put 1 for alpha and 0 for beta. Alpha and beta come from the kernel's mathematical definition, where the resultant matrix C will be equal to alpha times A times B plus beta times C. So if we let alpha equal to 1 and beta equal to 0, it's similar to C equals A times B syntax-wise. And if we let alpha equal to 1 and beta equal to 1 as well, it's similar to C plus equal A times B. Now that we're finished initializing our kernel, we can start encoding commands to the command buffer. And in order to do that is to use the kernel's encode function. For the command buffer parameter, we can use the one that we created. But for the left, the right, and result matrix parameter, we need to create new MPS matrix instances. So we can start with the left side matrix. And we're going to initialize it with the method that requires a metal buffer. And we need the metal buffer so that we can reserve memory. And that allocated memory will be accessible to the GPU. We also need to make an MPS matrix descriptor. And this descriptor class describes the matrix. In order to create our metal buffer for matrix A, we need to use our metal device's makeBuffer method. And we need to choose the one that has bytes so that we can insert matrix A's data. So let's go ahead and make up some values for matrix A and B. And then I'll explain the length and options parameters. For our left matrix values, which I'm going to use a float 32 array, I'll use 2, 7, 1, 8, 2, and 8. I'm using float 32 because the GPU is going to be performing single precision operations. And for our right matrix, I'll use the values 3, 1, 4, 1, 5, and 9. And as you can see, I tried to mimic how the matrix data entry looks like. But it's also important to know that all matrix data given to the MPS matrix is interpreted in row major order. And inserting data into memory in row major order is done by inserting the entries of the row vectors in the matrix. Now that we define our entries for the left and right matrices, we can finish creating the left matrix buffer. So the length parameter takes an integer value, and this integer value will be the number of bytes that we want to allocate. And in this case is the amount of bytes that's in our matrix A entries array. And in order to determine the amount of bytes that's in the array, we need to determine how many bytes each value in the array uses. So each value in the array is a float32 type. And what this means is that each value will take up 32 bits of memory, or will take up 32 divided by 8 bytes of memory, which is 4 bytes. And since we have an array of this type, each value in the array is going to take up 4 bytes. So we can just add up the bytes to get our total bytes length, which is going to be 24 bytes. But instead of just inserting 24 bytes, I can use the memory layout enumeration. With this, I can use the float32 type as an argument and get the amount of bytes it uses. And since I'm allocating memory, I should use the stride variable. Then we can multiply that by the count of the array. So for the length parameter, I'll insert the total bytes. The options parameter takes a metal resource option structure. With this, you can pick what can access the memory, and I'm going to choose the default option, which is storage mode shared. This option allows the buffer to be accessed by the CPU and the GPU. Then we can use it for the buffer parameter, which is an optional, so I'm going to force unwrap it. Now we can make our MPS matrix descriptor instance, and in order to do that, we need to use the MPS matrix descriptor initializer, and pick the initializer that has the rows, columns, row bytes, and data type parameters. For rows, we enter 3, and for columns, we enter 2. For the row bytes parameter, it needs the total bytes in a single row, so we can use the total bytes used divided by the amount of rows it has. And then we'll put float32 for the data type. Now we can finish initializing our MPS matrix by inserting the descriptor into the parameter. Now we can start making our right side matrix, which is B. And B is going to be initialized the exact same way as A. But instead of having 3 rows and 2 columns, B has 2 rows and 3 columns. And the resultant matrix C will be set up differently, only in that when we set up its buffer, we're going to initialize it with all zeros, by not using the initializer with the bytes parameter. And the amount of bytes that C has is matrix A's rows multiplied by matrix B's columns multiplied by the stride amount. Now that we have matrix A, B, and C initialized, we can finish initializing the kernel. Then we can send it to be processed by the GPU by committing it on the command buffer and wait for it to be completed before moving on. So that's basically how to multiply 2 matrices together on the GPU. Now, to view the results of the operation in matrix C, we need to get a pointer to its buffer. Then we need to bind the pointer to a type and size, and then we can create a new buffer pointer using the type pointer and size. And then I'm going to map the buffer pointer and append the value to the output float32 array. And when I print the output and run it, everything looks correct. I'll even do a little pretty print for how the matrix would appear on paper. So there you have it. Thanks for watching. If you like this video, you can subscribe to my channel to support it. Also, if you have any comments about the video, you can leave them below.